This chapter on electric circuits is super long. We're still dealing with electrical circuits. I want to remind you that we've earlier discussed the concept of resistor voltages. The resistor voltage of a current carrying resistor is just the product of I times R. I show a pair of resistors in parallel. I don't show the rest of the circuit, whatever it might be, it doesn't matter. We have current approaching that branch point, and it divides, not equally in general, some going to the upper branch, some going to the lower branch. My purpose in having you look at this diagram is to use it to prove the following statement. The resistor voltage across or in each of the resistors that are parallel to each other are all the same IR for each of the resistors in parallel. Let me prove that to you using the loop rule, or otherwise known as Kirchhoff's law. I've labeled 4 points around this pair of parallel resistors, A, B, C, and D. I've indicated that the current through R1 is I1, and the current through I2 is in the same direction. We call it I2 through resistor R2. Let's go around the loop A, B, C, D, A. Start here, go with the current arrow, come around, go against the current arrow, and arrive back at our starting point. By the loop rule, the sum of the signed voltages encountered is 0. And so through R1, we're going with the current arrow. The signed resistor voltage is I1, negative I1R1. Negative because we're going with the current arrow. Maybe you forgot that rule. And then we come around and head in the direction opposite to that of I2. And so we have a signed resistor voltage of positive I2R2. The sum of those two resistor voltages is 0. This equation makes it quite clear that I2R2 equals I1R1. Or in shorter form, we can say that V2 equals V1, where V represents two things in this chapter. It's either the abbreviation of the word volt, that's not the case here, or it's the symbol that we use for a resistor voltage. Well, let's use the fact that resistor voltages for resistors in parallel are the same. Consider the case of the branching of the current that approaches a pair of parallel resistors. We have two resistors in parallel, a 3 ohm and a 6 ohm. 18 amperes approaches the branch point there. Some of the current goes upstairs in the upper branch, call it I1, and the rest, I2, goes in the lower branch. You have had ample experience, perhaps, using the other divided by the sum rule. The current, for example, in the upper branch is a certain ratio or fraction times 18. And that fraction, or that ratio, is the other resistor, or resistance, 6 ohms, divided by the sum of the two resistances, 3 and 6. So it's 6 over 9 times 18. 9 goes into 18 twice, times 6. Final result, 12 amperes. We don't have to do the same kind of other divided by the sum rule for the lower branch, because we know the total current is 18. And if we have 12 upstairs, what's left is 6 downstairs, 6 amperes downstairs. I won't record that fact up here. But there's another way to get the current in each of the two branches without using the other divided by the sum rule. we'll use what we just learned about the resistor voltages of resistors in parallel are the same, top and bottom. Well, let's apply that fact that the resistor voltages are the same. We have for the upper branch here, I times R is 3 times I1. It equals 6 times I2. Solving for I1, we see that I1 is twice of I2. But we know also that the sum of the two currents, I1 and I2, is 18. The sum is 18. Let's go up here. The sum is 18. Well, we found just half a minute ago that I1 is twice of I2. So replace that I1 with twice I2, join it with 1 times I2 to get 3 I2 equals 18. Final result, I2 is 6 amps, and I1 is 12 amperes, which is what we found using the other method. Use which other method you like. But what will you do if you encounter more than 2 resistors in parallel? There is no other divided by the sum rule that I showed you that will account for 3 or more resistors in parallel. You only know how to do the other divided by the sum rule when you have just 2 resistors in parallel. So let's look at the 3 resistor in parallel situation here. I show current approaching a branch point with 3 branches, upper, lower, and middle. I'll call the current that's unknown in the upper branch X, middle branch Y, lower branch Z. We're going to assume that the current that's approaching the branch point here is 12 amperes. And we'll make use of that fact soon. Let's arbitrarily compare the top and the bottom resistor voltages. So you have 2 times X equaling 6 times Z. 2 times X equals 6 times Z, so X is 3 times Z. Let's put that aside for a moment, and let's arbitrarily choose to compare the middle with the bottom. So we have 3 times Y equals 6 times Z. 3 times Y equals 6 times Z, so Y is twice Z. So now we have X in terms of Z and Y in terms of Z. And now we'll put to use the fact that the sum of X, Y, and Z is 12. So that's 3Z for X, 2Z for Y, and a Z for a Z. This adds up to 3 and 2 is 5 plus 1, 6Z equals 12. Therefore, Z equals 2 amperes. And now that we know what Z is, we can go back to get X. X is 3 times whatever Z is, or 3 times 2, that's 6 amperes. And finally, Y is twice of what Z is, but Z is 2, so twice of 2 is 4. You can extend this procedure to more than 3 resistors in parallel, but that would be algebraically kind of unpleasant, so I'm never going to give you a problem with more than 3 resistors in parallel. I hope you learned something. If not, maybe you want to rewind and play this video again.